Hi everyone. I'm going to record a short video here just to finish the lecture on multiple regression. So in class today we got through a lot of the slides. We got through the graphical description of multiple regression. We got through the penguins example where we had a model that had flipper length, bill length, and bill depth to predict body mass. So we gathered our variables, we looked at the correlation plots, we built a full model with all three variables in it, flipper length, bill length, and bill depth. We looked at the output that gives us the slopes and our f-test on the model as a whole. We checked our assumptions, normality, homoscedasticity, and we didn't talk about collinearity except to say what it was, but you should read the textbook on that. And we talked about how to interpret the output. The intercept, it's usually not much interest to us. It's really the slopes that are the most interesting part of the model because they tell us how these different predictor variables, these different independent or x variables, how they relate to the dependent measure, the y variable that we're trying to predict. We talked about standard error of the estimate, which is in units of the predicted variable. R squared is just like in bivariate regression. It's the proportion of variance in the dependent measure that's accounted for by the model as a whole. And that's what this p-value test of. It's a test, a rather coarse test of the model as a whole with all three variables in it versus a model with no x variables and only an intercept. So it's usually going to be significant. The adjusted R squared we'll talk about now because that's one of the ways we can use to refine our model. So we talked about the principle of parsimony in science. It's better to have simple models when we can. And we talked a little bit in class today about the trade-off between including more x variables in the model and having to pay, as I sort of described it, pay using a degree of freedom. So each time you add a model, you account for some of the variability in the data, in the predicted variable, the dependent measure, y. And each time you add a new x variable, you're accounting for some new portion of variance that wasn't accounted for by the first variable, like this purple bit. But there's also some overlap in the variance that's accounted for by the two x variables. And the more x variables you add, the likelier it'll be that you're in a situation where one of the x variables, in this case x1, no longer ends up contributing a very large, unique portion of variance to the model. And so now the question is it worth it to keep it in the model or not? We talked in class today about how the F statistic is a ratio of two things, and each of those two things are also ratios with degrees of freedom on the bottom. I won't go back over that now. But the basic idea is each time you add a variable, you take a degree of freedom from the denominator of mean squared residuals, and you move it up to the denominator of the mean square model. And so the result of that is this gets bigger and that gets smaller, all other things being equal. So to offset that change, you need to have some explanatory power of that x variable that offsets the decrease in this ratio. And that's what the trade-off is between a complex model with lots of predictors and a simple model with few of them. So we quickly at the end of the lecture today talked about 4 ways of adjudicating whether or not to include a variable in the model. Adjusted R squared, which we'll look at now. The AIC, Akaike Information Criterion. This is what's used by default in R's step command, which will do stepwise regression, which we will talk about today. And there's two other ways people can do this. We won't talk about that today or in this course. We'll focus on these first two, adjusted R-squared and the AIC. No matter which way you do it, all of these procedures share the same common concept, which is you first have a full model that contains all the variables that you might be interested in, and you compare that to a reduced model in which the x variable that you're testing is removed. So like I said in class, it's like having a pizza, all dressed, everything on it. It tastes great, and you want to know, do I really need the pepperoni? So to test that, you take the pepperoni off, and now you compare the pizza with everything, including pepperoni, versus the pizza with everything except pepperoni. If the two taste just as good, you don't need the pepperoni. Okay, adjusted R-squared is one of the outputs you get in the multiple regression, and you'll notice it is a bit smaller than the main multiple R-squared. And the reason is the adjusted R-squared, the formula is up here. So the formula for R-squared is 1 minus sum of squares residuals over sum of squares total. We've seen that formula before. The formula for adjusted R-squared, it's basically the same, except this sum of squares ratio is multiplied by this other ratio, n minus 1 on the top, n minus k minus 1 on the bottom. N is the number of observations, k is the number of x variables. And so you can see, if k was 0, then it will be n minus 1 over n minus 1, which would be 1. So this would just be the same as R-squared. So a model with no variables in it, just an intercept, the adjusted R-squared is the same as R-squared. Each time you add an x variable to the model, k increases by 1. And this ratio here on the right becomes n minus 1 over n minus 1 minus k. So n minus 1 over something a little bit smaller than n minus 1. So this becomes a quantity just a little bit larger than 1. So you're multiplying this sum of squares ratio by a quantity a little bit bigger than 1. So you're boosting it up a bit. So it's 1 minus a boosted up version of this, which means that R-squared, adjusted R-squared will be a bit smaller than R-squared, which is what we see. And so the way that adjusted R-squared is used is adjusted R-squared will only increase from one model to another model if the new x variable that you add improves the model performance more than what you'd expect by chance. So if you take a pizza without pepperoni and you add pepperoni, if adjusted R-squared increases, then the pepperoni is worth it. If the adjusted R-squared does not increase when you add pepperoni, you don't need the pepperoni. Clearly, I'm still a bit hungry. So here's an example in R. We'll start with a full model. We have body mass is the dependent variable, and flipper length, bill length, and bill depth are our three independent variables. We estimate the model with the lm command. We send the output to mod.full, and then we look at the summary. And we're looking at a part of the summary. We're just looking at adjusted R-squared. And that $sign is a way of indexing into the summary and saying, just show us the adjusted R-squared. And the adjusted R-squared for the full model is 0.498158. Now we make a different version of the model called model.red for reduced, a reduced model that's the same as the full model, except bill depth is missing from the reduced model. We take that's the pepperoni. We take the pepperoni off the pizza. We fit that new reduced version without bill depth, and we look at the summary adjusted R-squared for that reduced model, and it's only 0.386. So it went down when we removed bill depth. That means we should keep bill depth in the model, because when we remove it, the adjusted R-squared gets worse, it goes down. So that means build depth is worth it to keep in the model. The pizza needs the pepperoni. If build depth was not worth it, then adjusted r squared would not have gone down. It would stay the same or even go up. Okay, so you take something out of the model that you're testing, whether it should be in or not, and if adjusted r squared goes down, then you need to keep it in the model. If adjusted r squared didn't go down, then you could keep it out. Okay? So the other way, the other metric that's used is the AIC metric. And this is not the exact formula for AIC. The exact formula is a bit complicated, and we don't need to go into the details. But this is more or less what it's proportional to. It's proportional to the sum of squares residuals, which is an error term, divided by sigma hat squared, which is a measure of variance, plus 2 times k, where k is the number of independent variables. K is the number of x variables in the model. So the reason I'm showing it to you is because you can see that it trades off 2 things. It includes something about the model fit, the error term, and it includes something about the number of x variables, 2 times k. And so we don't need to get into the gritty details, but the basic bottom line is lower AIC values are better. When an AIC value gets lower, that means whatever you did to the model, whether you added something or took something away, it's a better model. So the better models have a lower AIC value. Okay, so now that you know that, here's what we can do very easily and quickly in R to refine our full model. So we saw with adjusted r squared how you could test individual terms sort of by hand. We're going to use r's step command, the step function, to automatically test every single term in the model to see if it should stay or go. Now, excuse me, step can do 3 flavors of model refinement. We can do a forward stepwise procedure, where we actually start not with a full model, but we start with an empty model with just an intercept, and we add x variables one at a time. Or we could do a backward stepwise procedure, where we start with a full model with everything in it, and we take away x variables one at a time and test whether they should stay or go. But there's also an option for the step command called both, which does a combination of forward and backward. And that's actually the most preferable option. So why? Why do we need to go sometimes forwards and sometimes backwards? Well, let's look at our Venn diagram again. So the big circle is the total variance in the dependent variable y. Let's say we add an x variable x1. That's how much variance is explained. It's quite a lot. So we should keep it. Then we add another x variable, x2, and it overlaps with x1, but it has enough unique variance that it accounts for that it should stay in the model also, so we keep it. So we're going forwards now. Forward we add x1, forward we add x2. Let's add x3, another forward step. It accounts for a goodly sized unique portion of variance in y, so we keep it. So we're going forward. We did 3 forward steps. Now notice what happened to x1. We saw this earlier in the lecture. Now that we added x2 and x3, they overlap enough with x1 that the amount of variance that x1 uniquely accounts for is really small, and it might not be worth it to keep that in the model anymore. So we need the possibility of taking a backward step where we remove a variable from the model. So the basic idea of stepwise is that you add a variable, you add a second one, and then you do a check. Now that I've added 2, should each of them stay? Yeah. Okay, let's add a third. Now that I've added a third, should each of them stay? x2 should stay, x3 should stay, oh, maybe x1 should go. So you take x1 out. Then you might add x4, and then you would do a check. Now that x4 is in the model, should x2 stay? Should x3 stay? Should x4 stay? Yes or no? You don't usually put a variable back in once it's been taken out. So if you took out x1 in a backward step, it would stay out. Now, this all happens automatically. We don't need to make these decisions by hand. The step function in R will do this for us. Here's how we would do it. First, we define a full model that contains all three x variables, flipper length, bill length, and bill depth. Then we define an empty model with no x variables, just an intercept. And the notation for defining a model with just an intercept is we say the dependent variable, squiggly, tilde, and then the number 1. The number 1 is a way to tell R, we just want to model a constant, an intercept. We don't need to model a variable with a slope, we just need to model a constant. And R will estimate the value of that constant, which won't end up being 1, it'll end up being the mean of body mass. So we have a full model, we have an empty model, and now we issue the step command. And what we do is we give it the empty model to start with. So we start with an empty model, and then we give it an argument called scope. And scope is a list that contains two things. We say lower equals mod.0, upper equals mod.full. That basically tells the step command what are the boundaries of our regression model. The emptiest it can be is the empty one, mod.0, and the fullest it can be is mod.full, the full model. So we start with the empty model, we give it the scope of how full or empty the model can get in principle, and then we say direction equals both. And that will force it to do forward steps and backward checks as well. Okay, so we define a full model, we define an empty model, and then we issue the step command with the option direction equals both. Once that happens, you'll see a long list of output, and I'll show you a demonstration of this in a second. Step starts with the empty model and adds, first it adds the best single variable that most reduces AIC. Remember, a lower AIC means a better model. Then it adds the next best variable that most reduces AIC. Then it does a backward check to see if dropping any of the current variables in the model helps. Then it adds the next third best variable to the model, and then goes back here and does a backward check. And it keeps going forwards and backwards and forwards and backwards until basically no more improvements are possible. Nothing it can do, adding or subtracting, nothing will reduce the AIC. Remember, a model with the lowest AIC wins. Okay? Let's look at an example in R. Where are we? Okay, so let's library tidyverse, library Palmer penguins, and let's go back and fetch our full model code, copy, paste. Uh-oh. Oh, right, pdata. I had I have to go and find that code. Where is it? Pdata, there we go. Dplyr gather variables. We'll copy that, we'll go back here. Okay, pdata equals blah, blah, blah. There's my data frame. Now we're going to define our full model. Good. And we'll define our empty model, mod.0, and it doesn't depend on any x variable, just on a constant. And 1 is the notation. Okay, and let's flip back here. Model refined equals step. Start with the, oh, we'll go back, sorry. we'll take that one. We'll start with the empty model. Step mod.0, we'll define our scope. It can be, on the one hand, totally empty, on the other hand, totally full, and direction equals both. Now when I hit enter, it's going to automatically cycle through all of these steps, and at each step, show the output. Oh, it didn't do that many steps. Okay, it started with an AIC of 1851.68. So where did it start? It started with an empty model. So if you don't include anything in the model, the AIC is 1851.68. If you then add the build depth variable, you can see the AIC goes down a little bit to 1792. Okay? If you then add, so this first step is asking the question, which of the three variables should I add first? And so it adds each one individually, one at a time, and computes the AIC, and the lowest one is build depth. So the step procedure is concluding, okay, my first forward step is to add build depth. And you can see that's what it did. Its first step is to add build depth, and it lowered the AIC from 1851 to 1792. Okay, now what is my next forward step? Well, I could add build length, and it does that. I could add flipper length, it does that. I could do nothing, or I could take away build depth, which is the only thing in the model right now. So those are the four possible moves. Now, which of those moves results in a lowering of the AIC, or the biggest lowering? Well, adding build length. So that's my next step. I now have a model with build depth and build length, and it has the lowest AIC I've seen so far. So now that I have those two in the model, what are my possible moves? Well, I could add the third one, flipper length. I could do nothing. I could take away build length, which I just added. I could take away build depth, which I added in the previous step. And here are the AICs for those four different moves. And which of those lowers the AIC the most from 1763? This first one, adding flipper length. So that's my next step. I add flipper length to the model. And now I have a model with all three variables, and it has this AIC. So now that I have all three in the model, what are my possible moves that I could make? Well, I could do nothing, which keeps the AIC at 1750.52. I could take away flipper length, which increases AIC above 1750, so that's bad. I could take away build length, that increases AIC even more. That's a worse move. I could take away build depth, that's an even worse move. So the best move of my possible moves now is to do nothing, which means the stepwise procedure is done. So in this case, the stepwise procedure, it started with an empty model, and it started adding variables one by one, and always doing a backward check to see if it should remove stuff. And what it ended up concluding is I should have a model with all three variables in it. All three are worth keeping in the model. So that's the answer to the model refinement, right down here. The answer is, that is my refined model. It's a model with everything in it. Now, it won't always turn out that way. Often you'll find out that the refined version of the model is some slightly reduced version of the full model. Some variables can be taken away. In this case, they're all in there. So that was starting with an empty model. It's also possible to do the other way around. Start with a full model, still define your scope as before, still say direction is both, but you start off the stepwise procedure starting with a full model. So let's just do that to compare. Okay? So model refined equals step, model full, scope equals list, lower equals mod 0, upper equals mod full, direction equals both. So it's the very same principle, the same considerations are done, except now we're just starting from a full model. And what happens? Not much. It's kind of like we're starting from this place right here. We start with a full model. The AIC is 1750. And what are our 4 possible moves? Well, we could do nothing. We could take away each variable individually. And anything we do, it gets worse. So we should do nothing. We should stay with our full model. So in this case, starting with an empty model and doing a stepwise procedure gets us the same answer as starting with a full model and doing a stepwise procedure. That's usually the case, but it won't always be the case. Okay, so we talked about using AIC. We talked about using adjusted R-squared if you want to do it by hand. I also mentioned p-values. We talked about a forward procedure, backward procedure, stepwise, starting with a full model, starting with an empty model. How do you decide what to do? Well, the real answer is there's no single correct answer. These are all different approaches to achieve the same outcome. They all involve the same concept, but it's a bit of a gray zone. I think in general, what you should do going forward is adopt whatever convention that's used in your lab or in your field of study or in the journal you're submitting to. But you should also ask questions. You should ask questions of your supervisor and your co-authors and colleagues. You know, if this is the way we do it, why? Why do we do it that way and not some other way? And hopefully there'll be an answer to that's acceptable to you, but sometimes there won't. And you might find yourself preferring to do it a different way. And that's fine. If you can report what you did and report why you did it that way, then you'll be standing on solid ground. For this course, in homeworks and exams, I will specify what flavor, what procedure I would like you to do. And it's going to be AIC if it involves stepwise procedure, and it'll involve adjusted R-squared if I ask for that. So just be familiar with how adjusted R-squared works and be familiar with how the procedure involving AIC works. But you're not going to have to calculate these by hand, and on an exam you're not going to have to write R code. I'll show you some output from a stepwise procedure, and I might ask you questions about it. Very high-level conceptual questions. Okay, so our full model, our refined model, included all 3 of these x variables. And just like in bivariate regression, we can now use the model to make predictions. So let's say we observe a new penguin that isn't in our data set yet, and it has a flipper length of 200 millimeters, a bill length of 46 millimeters, and a bill depth of 22 millimeters. According to our model, how much would it weigh? How much does it weigh? Well, now that we have a model that models weight as a function of these 3 things, we can estimate this penguin's weight using our model. So we can simply create a new tibble, a new data frame, and we have to name each variable using the same names that are in our model. Flipper length mm equals 200, bill length mm equals 46, bill depth mm equals 22. So it creates a tiny little tibble with just 1 row and 3 columns. And then we use the predict function. We feed the predict function our refined model object, our final model, and this new data frame we just created, and it spits out 4,789.586. According to our model, this penguin with these characteristics is predicted to weigh 4,789.586 grams. This 1 that R spits out above the output, you can ignore that. It's a bit of an annoyance in R. It's this number that is the one that you're interested in. Now remember from our summary from a few slides ago that for this model, the standard error of the estimate is 324.9 grams. So that compared to the predicted weight, it gives you a bit of a concrete idea of how good your model is. Maybe a little better than 10%. Okay, this is the slide I showed at the end of the course, but I'll go through it again just to, because I was a bit rushed when we talked about it before. This course is about linear models, and basically everything we do in this course is one flavor of linear model. You can imagine starting with a linear model that literally has nothing in it except randomness. So this is a linear model that says my dependent variable y in the population equals 0. And in my sample, any non-zero values are only attributable to epsilon, which is random variation. If we add a single parameter, beta 0, to the model, now we have an intercept. Now we're saying our population variable y is equal to some non-zero parameter, beta 0, plus random variation. And what is beta 0? I don't know, but I can estimate it based on my sample. The estimate is the mean of the sample. I can add an x variable that has a slope, beta 1, and now my model of y in the population is that it is equal to some mean, beta 0, plus some slope, beta 1, times the value of this other x variable, plus random noise. And I can add a second x variable, and now I have multiple regression. I could add a third x variable, and a fourth, and as we saw, we can add k x variables to our multiple regression model, and it's the same basic idea. Here's what that looks like graphically. If we have a model with literally nothing in it except random noise, epsilon, that's kind of like saying, my model of this population variable y is that it's really 0. And any departure from 0 in my sample is due to random noise, random variation. This version of the model with a single parameter beta 0, a constant, looks like this graphically. Now I'm saying, I think my population variable y is equal to beta 0. And any variation around beta 0 is random noise, random variation. And what is beta 0 in the population? I don't know, but I can estimate it based on my sample. It's the mean of my sample. This version now says the y variable in my population is equal to some constant, beta 0, plus some slope, beta 1, times x, this x variable. What is beta 0 and what is beta 1 in the population? I don't know, but I can estimate them based on my small sample. And that estimate is what you get when you do a linear model. And any variation vertically around that line is assumed to be random noise, random variation. And of course I can have multiple x variables, and I get, if I have 2 x variables, I get a plane in 3D, and if I have more than 2, I get a hyperplane in k-dimensional space, which is hard to visualize. Actually, it will be k plus 1 dimensional space. Okay, and we'll see later in the course with ANOVA. ANOVA is also a form of linear model, which is handy. It's handy to see that because it will help us understand how things work. Okay, I hope that helped tie things up a bit. So we went over how to refine a model using adjusted R-squared, and then we saw how to do it kind of automatically using the step command, which uses AIC. And I showed you a concrete example in R. So the homework will get you doing some of this stuff. Ask questions of your TA if you get stuck, either on R code or on the concepts. And failing that, don't hesitate to get in touch with me. Okay, thank you and see you next week.